We are back with another episode of the New Stack Agents, our show about all things AI. And this time I think for the first time, we're talking to a model builder, actually. So this time we've got Stefano Ermon. Is that how you pronounce it?
That's right.
Awesome. Stefano Ermon, co-founder and CEO of Inception Labs, and really timely that we get to talk to you because only yesterday you launched the last version of your model, which is a diffusion model, which is quite different from the models most people probably think about when we think about large language models. But before we talk about all of that, I really want to just talk about you because you've got a really interesting background as well. So maybe you can talk a little bit about how you got into this space and
of course. Excited to be here. Thanks so much for hosting me. I'm Stefano, one of the founders and the CEO of Inception, where we're building a new kind of LLM that is based on diffusion. And the way we got there is through a journey that basically started at Stanford in my lab about 10 years ago or so. So I got my PhD in computer science. I started working so I've been working in AI for a pretty long time now. But the interesting bit is that I was working in a field called generative models since basically when I started my PhD, and that's the kind of field that eventually became what we now call generative AI. And so we were thinking about ways to get machine learning models not to just classify images or emails or the kind of like typical tasks that people were using machine learning for, but actually to generate content, generate images, generate video, generate text. And that's always been my passion. It's always been kind of like my whole research group at Stanford has been working on that topic, on that research direction, and that's what ultimately led to me starting Inception and working on diffusion language models. The way I got there is that, for the longest time, I've actually been working on image generation. So again, like building generative AI solutions that can create new images based on a caption, for example, or some other kind of signal, some other way of controlling what you want the model to generate. And I guess for a long time, the field was dominated by an approach called generative adversarial networks, where you have these two neural networks, and one is generating images, and the other one is trying to classify them. Is this real? Is this fake? And then you have this game that you play against each other, and that's kind of like how you used to train these models. And they kind of worked, but it was very, very unstable to train in practice because there's this game, and it's a very, very tricky kind of like optimization problem to solve. And so in my lab, we kind of proposed this alternative approach, which is now called the diffusion model. Back in 2019, that was, where instead you generate images by kind of like gradually removing noise. So you start with pure noise, and then you use a neural network to refine the image. So the network is trained to fix mistakes, remove noise, and then you keep applying this network over and over until you get a nice, crisp, beautiful image at the end. And that basically took over very quickly the whole field. People quickly realized that that's a much better solution. It was very scalable, very easy to train. The results were very, 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 very high quality. And then essentially, the whole Stable Diffusion started, and Midjourney and all the a bunch of big models trained on that approach started coming out, and they took over basically the internet, and then the whole even me, like more broadly, like everyone now is got to experience the power of these generative AI solutions.
Yeah, and that's probably where most people heard about diffusion as a term for the first time. Stable Diffusion being one of those early models that were out there, right?
Exactly.
Why was that early on? Why was diffusion so great for images? Why didn't, or maybe people did already think about generating text that way at the time as well?
Yeah, so including in my lab, immediately we started kind of like trying to see, okay, how can we get these models to also work well on text and code or DNA, anything that is a little bit more discrete. And that's the fundamental difference. An image, it's just a collection of pixels, but it's pretty naturally thought as a continuous type of object, right? You can kind of like interpolate between two colors and things still make sense. there is no really a good way to interpolate between two words, right? Things in between don't necessarily make sense. So it's a much more discrete kind of geometry where you jump from one meaning to another one, and there is nothing in between. While if you think about images, there is always a way to kind of like interpolate, and you can combine kind of like two images, and they still sort of like make sense. And so a lot of the math that was developed for diffusion models on continuous spaces did not really apply to discrete objects, text, code, again, DNA. So it took up several years to actually figure out how to do it properly. And a lot of researchers tried. The key breakthrough was, again, a paper from my lab at Stanford that we published in 2024. And essentially, for the first time, we were able to show that a diffusion model trained on language and text was actually essentially producing results of quality equivalent to a model of the same size. This was still like a GPT-2 size model. So you take a GPT-2 model and you train it as an autoregressive model, which is the way everybody else is training LLMs, and you train it as a diffusion model. And the result was, finally, with those improvements that we made, the quality was the same, but the key advantage of the diffusion model was that it was 10x faster.
Right. The speed is definitely one of the big differences here.
Yes.
But talk to me for a moment about what led to that breakthrough. Like, explain it to me like I'm 5, basically, right? Because I'm sure the math is well above my head.
Yeah, no, unfortunately, there is a lot of complicated math in terms of like figuring out what's the equivalent of a diffusion process over a graph, and a lot of it's somewhat complicated, but it boiled down to a different way of training the models. Okay. And a different way of using the models to figure out how to go from basically random text into what you would want the model to output, like coherent text that is actually answering the question that the users want to get answered. And so fundamentally, it corresponds to a very different way of training an LLM. Like a typical autoregressive LLM is generating text left to right, one token at a time. The model is trained to predict the next token. So it's fundamentally the same technology that you all have, that we had on our phones for a long time. Like the thing that predicts what is the next, how you should use autocomplete. Effectively, it's like right. Fancy autocomplete. That's what's behind all the.
Some people will be offended if you say that, but that's what it comes down to, right?
It is a fancy autocomplete at the end of the day, right? And then just like a much bigger model, training on a lot more data, but fundamentally that's the idea. And the diffusion model is very different. There is still a big neural network, but the network is not trained to predict the next token or the next word. The network is trying to fix mistakes. And so you kind of like start with clean text or code, and then you add mistakes, and then you train the network to fix the mistakes. And that's a much more global view of the text that you use to train the models, where you're able to use context to the left and to the right to figure out where the mistakes are and how to fix them. And then at the inference time, when you ask the model a question, the way the model produces an answer is also very different. It's not generating the answer one word at a time, left to right, but it's actually starting with a full answer, which is a rough approximation of what you want, and then it refines it over and over until it's sufficiently high quality. The same way the Stable Diffusion used to work on images, just applied to text. And the key benefit is that the neural network has this global view. It's using context to the left and to the right. It's able to modify many tokens at the same time. So in the autoregressive world, you need one of these massive neural networks with trillions of parameters. You need to process all of this stuff, and then you get a single token. In a diffusion language model, you still have a big neural network, and you still have to go through it. But at the end, you're able to get multiple tokens. And so you get more outputs for the same amount of work. And that's why these models are so practiced a lot faster than competing autoregressive models.
And maybe before, and I think a lot of people maybe remember seeing that with Stable Diffusion, how kind of the images crystallize almost from just blobs into what you were looking for, hopefully. yeah, maybe it's something in that direction with 6 fingers on a person, but still pretty close to what you want. You did mention, though, that the training is very different. So before we talk about the inference, I kind of want to talk a little bit about the training of these models, because we've seen a lot of advances in how large language models are trained, but how do you do it, and how has that training process changed too over the years, from training image models to now training these text models?
Yeah, unfortunately, a lot of the specifics of how the training works and the architectures and the types of data we use and the actual losses that we use are proprietary, and we're not able to.
I was afraid you were going to say that.
But roughly speaking,
high level.
It is not too different from how you would train a typical image diffusion model. Like there's a big neural network. We've shared publicly that we're still using transformers as the kind of like key building block for the neural network architecture. Although we don't have to. Like in principle, you can use any architecture that you want, but we are still using transformers. So it's not. It's an orthogonal choice. Like there's a neural network architecture, we can still use transformers. It's just trained in a different way. It's just trained to essentially fix mistakes as opposed to being trained to predict the next token.
Mm-hmm. Why does I keep thinking about this? Why does fixing the mistakes work so quickly? Why is it faster than predicting the next word?
So basically what happens is that if you want to predict, 1,000 tokens, in the autoregressive world, you need to evaluate a large neural network 1,000 times. That's this sequential computation, that's all, that you cannot get around it. You cannot generate the 10th token until you generated everything that comes before it. And so it's a kind of sequential computation that cannot be accelerated, essentially. But we live in a world where we have access to GPUs. And GPUs are parallel processors. They like to process many things at the same time. That's what they were built for. That's what they are good at. And so the key idea is that in a diffusion language model, you're kind of like getting the GPU to process many tokens at the same time. So you're actually processing all 1,000 of them at the same time, let's say. And so that's why you can be much more efficient, because the network is able to make many changes at the same time in parallel. So as long as you don't need too many refinement steps, that's the crucial thing. Because if you need a lot of refinement steps, then there's no benefit. But if the number of refinement steps is small enough, then this thing can be dramatically more efficient than a traditional autoregressive model. And that was kind of like the key result of the paper that I mentioned from 2024, which won the best paper award at the International Conference of Machine Learning, which is like the top machine learning conference in the world, was exactly showing that even with a small number of denoising steps, of diffusion steps, you still get results of the same quality as the autoregressive model that requires thousands of steps. And so that was really the insight that gave me confidence that this thing was going to work. And it was just a matter of scaling up and training bigger models.
Right. And enough confidence to launch a company around it. So that helps to a well-funded company at this point around it, which you do need funding to train these models. Now, you mentioned these steps, like these diffusion steps. How many are we talking about here? And like, is there at some point a diminishing return you seem to imply by adding more of those steps to? And how do you know where to make that cutoff?
Yeah, that's a great question, and that's again part of the kind of like proprietary inference algorithm that we developed at Inception. In practice, we don't need many diffusion steps, and that's why our models are so fast. The interesting thing is that, especially with the Mercury 2, which is the latest model that we released yesterday, is that like one of the ways people have been able to get most of the performance gains over the last year or so is this idea of test time inference and thinking models, right? And so if you've interacted with some of the latest LLMs, before they answer, they often spend a bunch of time thinking, right? And what thinking means really is that they generate tokens one by one that are part of a thinking trace that maybe are not then given to the user, but are helpful for the LLM to come up with the final answer. And so it's basically a way to use compute at inference time to improve the quality of the answer. And the only way you can do it with an autoregressive model is to just go through these long thinking traces where the model might maybe try out a candidate solution and then it backtracks and then it tries something else. And everything has to happen in the thinking trace. And the diffusion model can do things differently, right? Because kind of like the edits and the reasoning and the improvements can happen in place. So the model can iteratively refine its answer until it's sufficiently high quality. And so, again, this idea of being able to trade off compute at inference time for quality, it's really, really important because it's been the main axis that people have been using over the last, in the recent, few months and year or so to really get the best performance out of LLMs.
Sure. And since you talked about performance, maybe give us some examples where Mercury 2, the model you released just this week, and I saw some benchmarks where you compared it to Claude Haiku and Sonnet and kind of the standard models that we think about today that are coming from the frontier labs.
Yeah, so the quality of Mercury 2 is comparable to the speed optimized models from frontier labs. So Haiku models, Flash models, mini models from OpenAI. That's the equivalence class of models that we're competing against. So full disclosure is not yet at the quality level of the highest quality models from frontier labs, like the largest and slowest and most expensive models from frontier labs.
Sure.
We're not yet at that level of quality. But when you think about LLMs, you always care about three things. You care about quality, you care about speed, and you care about cost. And for some applications, perhaps you want the highest possible quality, you don't care about cost, you don't care about speed, but there is a lot of applications where you do care about latency. If you're interacting, you're building a customer support voice agent, it has to answer quickly. Or, you are using LLMs inside an IDE to help developers with coding suggestions, or you have an agent that is kind of like quickly refactoring code and interacting with the developer in real time, then you really, really care about speed. And that's the kind of settings where people use speed optimized models, or they deploy models on AI inference chips, ASICs that can be significantly faster than autoregressive models served on traditional GPUs. And what we're seeing is that our Mercury 2 model, which is a reasoning model, is actually able to match the quality of these speed optimized models from frontier labs while being 5 to 10x faster in terms of like the end-to-end latency, how long you need to wait before it gives you an answer. That's really opening up a lot of very, very interesting applications. Whenever you think about, again, coding agents, you think about voice agents, you think about search and information retrieval, where you need the LLM to rewrite queries, re-rank results, summarize results. There's a lot of applications where speed really matters. And that's where we're seeing most traction right now with Mercury 2.
Yeah, and we've seen some of the frontier labs also launch fast models that are often very, very expensive, because I'm assuming they run on even more compute than the regular models. So.
Yeah, I know OpenAI announced a partnership with Cerebras. Cerebras is building these specialized AI inference chips that are really, really fast.
Make it look small. They're gigantic chips, right?
Yes. Yeah. I've been to their office. Yeah, we know them well. So I've seen how the sausage is made. And but the problem with Cerebras is that it's a specialized inference chips. There is not it's the amount of capacity that they have is much more limited compared to just Nvidia GPUs, which are everywhere, very abundant, still expensive, but maybe much more abundant. And so the exciting thing is that we can approach the speed of the traditional autoregressive models run on specialized hardware by using a better algorithm, essentially at the software level. Something more parallel that can take advantage of GPUs and run really, really quickly, like over 1,000 tokens per second. That's the kind of throughputs we can get with Mercury 2.
And speed sometimes gets underestimated, I think, in this world, because it often just also means you can iterate so much faster on maybe an idea that otherwise would take forever. Now maybe you can just have multiple iteration steps. So.
Absolutely, yes. especially because we're moving towards this agentic kind of like type of workflow, where it's not just I ask you a question, you give me an answer, where maybe at the end of the day there's an upper bound on how fast people read, and so speed maybe doesn't matter too much up to a certain point. But if you start chaining multiple LLMs using tools to do something, and then use the results to do something else and plan and reason, then that's where it becomes a major bottleneck, right? And so if you can accelerate that, and the text is actually consumed by other agents or other tools, then speed really matters. And you care about, as you said, kind of like fast iteration cycles. That's what matters at the end.
And Mercury 2 can call tools, right? So it's got that ability
it's
as
a reasoning model. It supports tool calling, structure outputs, so you can use it whenever you would normally use traditional autoregressive LLMs. You can swap it out and use Mercury 2.
Mm-hmm. Now, are you making trade-offs in quality for speed, like some of the other models do, like the smaller models, like the Haikus, for example, or the fast models? Or could you just be slower and reach the same quality as like a Sonnet or Opus model from Anthropic or a GPT 5.3?
Not yet, unfortunately. But so there is a trade-off between quality and speed, so right now we're sort of like optimizing for latency sensitive kind of like applications and the kind of latency budgets that you would want to have for voice or fast agents. So maybe from 200 milliseconds to a little over a second, or somewhere a second and a half. That's kind of like the budget the kind of applications that we target. It's we made some choices in terms of like the size of the model and the way we designed the inference algorithm that is kind of like optimizing for that use case. But nothing is preventing us from going to the next step and training bigger models that are actually optimizing for quality. In fact, I'm very excited to see what happens, because maybe the quality is going to be even higher, right? Because we have this error correction kind of like built in. Who knows what's going to happen, right? It's still very early days. I think a lot of the competitors are sort of like building on top of the same technological approach, like it's all the same stack. They're all more or less clones of each other. What we're building is something very different that could potentially have, be much better in the limit, right? So that's why I'm so excited about this technology.
And it sounds like you're expecting that the size of the model and quality are correlated pretty directly, like they are with the other models.
We're definitely seeing that. We have our own scaling laws, and we're seeing this kind of trade-offs, which is not unexpected. I think it's just like you're finished statistical models, and we know that those things matter. We are seeing it. If I've been part of projects where we've built scaling laws for when we think about diffusion models for image generation or video generation. So it's not unexpected that you would see these kind of trade-offs.
For sure. When it comes to the inference, you were talking about running on GPUs. Is there anything else that changes at inference time, or do the bottlenecks change compared to traditional LLMs because you're faster? Or any differences there?
The key difference is that the reason autoregressive models are slow and expensive is that the computation is sequential. So you can process one token at a time, and what this means is that the computation is memory bound, meaning that what the GPU does is it's spending most of the time moving around the weights of the neural network through the memory hierarchy, from the slow memory all the way down to where it can actually do the computations.
Right.
So instead of doing what it's good at, which is doing a lot of essentially arithmetic additions and multiplications, it's spending a lot of time moving stuff around through the memory hierarchy, which to some extent cannot really be optimized up to a certain point, just because of like some physical limits in terms of like how quickly you can move information around.
Which is part why Cerebras puts the memory right on the chip, for example, right?
Exactly. So that's why there's so much pressure on more memory and more chips, faster bandwidth. That's the whole game, right? In a diffusion model, we're shifting that towards a compute bound regime, where because we're actually able to process many things at the same time, you're moving back to the kind of workloads that are really good for GPUs, where you're doing a lot of arithmetic. Like the arithmetic intensity can be as high as you want to some extent. And that's really the shift. That's what's enabling us to be much more efficient.
Interesting. So you're good friends with Nvidia probably because they love that architecture.
Yeah, Nvidia is an investor in the company. We work very closely with them. We have a very close partnership, and they're helping us really optimize the serving engine and helping us with kernels. So yeah, we are very close to Nvidia, and they've been an amazing partner in building out this technology, and they're very supportive of this approach.
I'm sure. If I'm a developer, does anything change for me when I switch out an endpoint from a regular model to a diffusion large language model?
No, it doesn't. That's the beauty of it. We've built everything to be backwards compatible. So it's all, we're actually able to serve models through OpenAI compatible endpoints. So it's literally like 2 lines of codes that you need to change to swap out an API key and change the endpoint URL, and everything works out of the box. So it's very convenient. If you want to give it a try, just sign up for an API key and try us out. It's going to be fast, and I'm sure you can deliver new user experiences. There's going to be a lot of interesting things you can do once you have access to a really, really quick model.
Yeah, I tried out the demo you have on your homepage yesterday, or on the Mercury 2 page at least. Nice. I forget where I saw it, but I was astonished by how fast it was, and the results were actually quite good too. So it's really quite the difference. When it comes to hosting your own models, was that a conscious decision that you wanted to be your own host as well and run your own APIs, or did you consider maybe just working with somebody else as a hoster for that? Or kind of
so that? Part of it was just like we had to build the serving infrastructure. Like you cannot serve these models using existing serving engines because the computation is so different. So we had to build our own serving engine, and so we kind of like had to do that work anyways. And so that's why we are serving the models ourselves through our own API platform. But I would want to say that we have partnered with AWS and Azure. So our models are actually available through those marketplaces. And so you can actually provision your own hardware, and you can run our models on your own GPUs and get the benefits. You can run them in your own VPCs, and so get all the privacy and security guarantees that are provided by our partners, by the big cloud providers, and you get the speed of our models. So Mercury 2 is not yet there, but we'll get it on the marketplace pretty soon. And so we do see a lot of value in kind of like getting distribution through these channels.
Of course. Would they, like in AWS, would they have to make quite a few changes to add this to kind of a hosted model marketplace like Bedrock, for example, then?
It is on Bedrock, so we did all the work in partnership with them. Yes. And so at the end of the day, it's all containerized, and we figured out a way to make it work with their infrastructure. But so yeah, all those technical difficulties have been solved, and at least the older generation of Mercury models is there. It's available today. You can use it, and we're working with them to get Mercury 2, which is the model we released yesterday, on the marketplace as soon as possible.
Got it. What about multimodal, since this technology comes out of image generation? How are you thinking about that with the models you're building?
Yeah, we definitely want to do that. It's on the roadmap. It's a very natural kind of like application for the technology we're building. As you said, fusion models are really, really good. As currently the state of the art for image generation, video generation, music. Now we're able to also do text and code. Why not just have a single big multimodal foundation model that is trained on all the different modalities? It can learn across these different signals, and it can do everything inside a diffusion model. So we're very excited about that vision. We're also a small startup, and so we have to be really focused, and we cannot do too many things. And so we've not been able to actually prioritize that effort. But it's in the roadmap. We'll get to that at some point.
But the changes you made to kind of the underlying math and computation wouldn't prevent you from also doing images. Would it actually, or maybe it would make the images better or worse, or kind of like?
That we don't know yet. That will be definitely work to be done. Like it's not as simple as just adding more data to the mix. But
Right.
we know we have ideas on how to do it. But it's not trivial for sure.
Sure, for sure. Now, as you were saying at the beginning, you were talking about the kind of how this is basically correcting what's, self-correcting constantly in a loop. Is there like a hybrid mode potentially between like a very smart LLM and a diffusion LLM, where the diffusion LLM comes in and corrects, or is it just a very dumb idea?
No, I think that could definitely be something that is worth exploring. I think I know that people have been exploring these kind of ideas for, let's say, video generation, where there's been some success in kind of like combining both architectures. Or maybe use an autoregressive model for the storyline, the high level concepts, but then you use a diffusion model to kind of fill in the details and get it from a rough sketch into a nice video. So
Right.
I think there is a lot of, we're just getting started. I think this is kind of like paving the way a little bit for new approaches, new things to try. Hybrid approaches could be quite interesting. It just becomes a little bit of, it adds complexity, which is always not the best thing, because then at the serving time, then you have two models and, orchestrating and synchronizing. It does add a lot of complexity at the deployment stage. So, if we can get a single model that can do everything, that would be a lot easier, a lot cleaner. But we'll see.
No, I hear you. A lot of times when I talk to startup founders, they do mention that it's hard to focus and know where to focus going forward, because there's so many things you could be exploring without giving away your roadmap or anything like that. But what are you exploring right now? Is there any kind of experiments you're interested in, or what are you thinking about going forward?
Yeah, we're laser focused on improving the speed, quality, cost, kind of like trade-offs that you get using different kind, and we're exploring many different paths to improve these trade-offs, improve the quality, improve the speed, further reduce costs, both on the training side, on the inference side, doing a lot of work at the systems level, like how do you actually optimize the kernels, how do you optimize the serving engine. So it's a stack. There is a lot of pieces that go into the full solution, and I think what's exciting is that we're again just getting started. So I'm sure that a lot of the choices that we made were suboptimal, and so there is still a lot of room for improvement. Like again, the existing autoregressive model, where I think there is a lot of diminishing returns at this point. A lot of the things have been tried, and there's not a lot of room for trying new things. This is still very, very early. There is a lot of low-hanging fruits, I think, are still there. So that's why I'm pretty optimistic that we're going to see big improvements over the next months and years by just pushing harder along to do R&D for diffusion language models.
Do you think that diffusion models could become the new default at some point, the new standard? Is that, I'm sure you're hoping for something like that, but do you think there's a possibility, or is it always going to be a speed quality trade-off at some point as your kind of both technologies improve?
Yeah, I absolutely believe that. I would not be doing this if I didn't. I think eventually it's all going to be an inference game. That's the only thing that will matter. The technology that scales better at inference time is the one that is going to win, the one that gives you the best tokens per dollar per watt kind of thing. That's the ratio that matters, of course, at a certain level of intelligence. And so that's the all the experiments and the early signals are pointing towards a trend where diffusion is superior. So if those trends continue to hold at larger scales, as we improve the intelligence of our models, then people will switch. I think it's just going to be the thing that makes sense economically, and so there is no reason for people to keep pushing on technology that is inferior. There's good reason to believe it. Like why? Diffusion is already the state of the art for images and videos, so it's not so unreasonable to think that it might become the standard also for text and code.
Yeah. And since there's already investments in that area in hardware as well, I'm guessing at this point that would benefit you because those stacks need to be built too, and videos are even more computationally difficult and costly compared to text. So,
Exactly.
We've talked a lot about inference. One thing we actually didn't talk about, I just realized, is post-training, or how you think about that, which I assume is also proprietary to some degree.
Yeah.
But we talk a lot about reinforcement learning, obviously, these days. I just wonder if that's similar to what you're doing. Or...
Yeah, so that was one of the key ingredients that went into the Mercury 2 model. We put a significant amount of effort to develop the infrastructure and the algorithms and the methodology to do reinforcement learning on a diffusion language model. As you know, the key bottleneck for reinforcement learning is inference. You're spending most of your time generating rollouts, getting the model to try out a bunch of things, and then you kind of score them and you see, what worked, what didn't, and you use that to make your model smarter, make your model better. But inference is the bottleneck for when you think about RL, and so that was obviously the thing we wanted to push on, because that's where we have the biggest advantage. A diffusion language model is much faster at inference time, is much faster at generating candidate rollouts, and as I mentioned, kind of like there's different ways of there's different axes that you can use to push test time inference with a diffusion model, the number of denoising steps, the length of the chain, and so it was a very, very natural place to kind of like take advantage of the unique aspects of a diffusion model. And that's how we got a lot of the amazing benchmark results that we announced yesterday. A lot of that is due to reinforcement learning.
That makes sense. Yes, that seems to be a lot of it.
Is that like in a diffusion model, you can use reinforcement learning also to just train the model to converge faster, which is also pretty unique to a diffusion model, right? It's hard to do in a traditional autoregressive model, but in the context of reinforcement learning, you can optimize for whatever you want. And so you can actually directly optimize for speed.
Yeah. Maybe we'll see those autoregressive models getting trained in the post-training steps with your models going forward to speed up the process. Yes. What does the competition look like for you? Because I think, as I said, at the beginning, the first time most people saw a diffusion model was when Google showed their efforts at, I think it was Google I/O or...
Yeah,
I think it was Google I/O, not Google Cloud Next last year. So about a year ago now.
Yeah.
So there are other labs thinking about this as well.
Yeah. And we're excited that other people are pushing in this direction. Our first Mercury model was actually released a few months before the Gemini diffusion. I think that
I'm sorry, I did not notice it.
Probably fewer people noticed, but I do think that was actually a forcing function for Google to actually get their models out. My understanding is that was an effort that had been going on for a while at Google, and then seeing other labs that were actually able to deliver a commercial scale diffusion language models must have played a role in terms of
I'm sure
getting them.
That's how that works these days.
To accelerate and release something. But yeah,
show something. I think I don't think they really ever released anything. Yeah.
Exactly, as you said, they have not actually released. It was a blog post. There was like a chat, kind of like playground where you can interact a little bit with the model. But as far as I know, it's not available in production to customers and developers. We're still the only ones that have an endpoint that it's publicly available. It's serving production traffic. It's used by developers and enterprises to build real world apps and things. So we're still definitely far ahead compared to the competition. But I think it's exciting. It's validating. I think that other players like Google, like Alibaba, like ByteDance are actually openly talking about diffusion for language projects that they have internally, I think a lot of people see the value in this approach, and so I'm expecting that trend to continue. I'm seeing that also in the academic kind of community. I was in NeurIPS, one of the big machine learning conferences in December, and so many papers now on diffusion for language. I think that the 2024 paper that we had really sparked a big kind of like effort in the space, both academic and industry, to see what's possible. It's very natural. Again, like we have this thing that works so well for some modalities. Why doesn't it work on text? How can we make it work on text? There are some obvious benefits. So it's exciting to see that other people are pushing in this direction. And as you said, I think that's the dream. Eventually, that this becomes the standard. I think that would be a really, really good outcome for us.
For sure. Now, do you still get to write papers? Do you still get to teach now that you're in this position?
We don't write papers much at Inception. I think we do try to publish some tech reports to give our customers and employees and prospective employees kind of like a sense of what's going on at the company. But it's a very competitive landscape, and so a lot of the IP is kind of like proprietary, and we're not able to share how we're training the models and the exact details of how how inference works. So that's a little bit unfortunate. I mean, I'm wearing my academic hat. I'd love to build knowledge and share it with the world, and then make progress as a field. But obviously, there are some commercial kind of like and business implications here and constraints that are hard to ignore. So at least right now, that seems to be the trend. All the big labs are also not publishing. So
which is a shame in a way, because early on there seemed to be like a lot of papers coming out, and a lot of what you're doing, not me personally, a lot of what's happening is because papers were published, right?
Absolutely.
Like the Transformer paper and your paper, things like that.
I mean, Google, contributed. The researchers at Google contributed a lot of really, really, really important ideas, and it was great back in the day when they were open about all the work that they were doing. I think that really accelerated the field.
Sure. But now you've got. What's your funding round? Almost 60 million, 56 million?
Something like that. Right? The latest round was 50 million.
So there's a lot of money involved now. So things change a little bit. Yeah, for sure. Is there anything we've missed? Anything that's exciting for you right now that we should talk about?
Yeah, the most exciting thing is it's definitely Mercury 2. I mean, it's very, very fresh. It just came out today. We are seeing, the feedback from the community was overwhelmingly positive. People are super excited about the speed, the quality. I can't wait to see what people build on top of these models. Lots of people are signing up on the API, building things, giving us feedback. So that's the probably the most exciting thing right now. And I encourage your viewers, your audience here to give it a try, see why it works in your workflow, in your applications. It's if you want to be at the frontier, I think this could be the next big thing.
Yeah, not everything needs to be an Opus 4.6 model, right?
Absolutely.
So, awesome. Well, thank you so much for being here. Appreciate it.
Yeah, thank you for hosting me. Yeah. This was a great conversation.
We'll keep this going as you launch new models going forward, and as this changes. So once you become the new OpenAI, we talk early.
Yes. That's the hope.
Awesome. Thank you.
Thank you.